Hello, everyone. Welcome to the webinar. We're just going to give a couple minutes for folks to get logged in, and we'll get going. Hello, everyone. Welcome to today's session, Building Decarb Tech Series, from the windows to the walls. My name is Katie Klusny. I'm the Associate Director at Illinois Green Alliance, and we're so excited that you guys are all here today for this session. Today's program was put on by Illinois Green's Programs Committee. It's a volunteer group that coordinates educational events covering a wide range of topics for the green building industry. The lead from the Programs Committee and moderator for today's event is Jason Meyering with Jason Meyering Architecture, and I'll be introducing Jason shortly. But before that, I wanted to introduce a few logistics for today and tell you a little bit more about Illinois Green. You've all been muted upon entry, so please type any questions you have into the Q&A, and I will get them answered at the end during our Q&A session. This webinar is also being recorded, and we'll be sending a recording along with PDFs of the slides and information for self-reporting instructions for continuing education after today's session. Just a little bit about Illinois Green. Illinois Green is a membership-driven nonprofit organization that advances green buildings and sustainable communities for all. Our 5-year strategic plan pushes the green building industry to meet or get on the path to net zero. And we achieve this work through educational events such as panels and building tours like today, engaging with communities and partnering with organizations across Illinois, and by advocating for new policies and legislation that advance green buildings. Our members can view recorded webinars on our on-demand library, and you can learn more about membership, see upcoming events, and get involved by visiting our website at illinoisgreenalliance.org. I want to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make our work possible. And a special thank you to our gold level sponsors, ComEd, Resource Innovations, and Sloan. Make a commitment to advancing green buildings and communities across the state. You can start a conversation about sponsor partnerships today at illinoisgreenalliance.org/sponsorship, or feel free and send me an email directly. And now I'd like to introduce Jason Meyering, our moderator for today's session. He's going to tell us a little bit more about what we're in store for today and learn a little bit more about our speakers. So Jason, I'm going to turn it over to you.
Thanks, Katie. Hello, everyone, again, and welcome to our next tech series discussion from the windows to the walls. I'm Jason Meyering, architect and member of the Illinois Green Alliance Programs Committee. With rising energy costs in our homes and businesses and increased costs of construction materials, new solutions are needed for greater impact and less expense and utilizing less materials. The fastest way to reduce our footprint and exhibits low embodied energy, low carbon emissions, and low cost is to retrofit. This tech series will discuss several options for converting, retrofitting, and replacing windows and wall elements for greater energy efficiency. Speakers will present research, data, and tools for you to utilize in reducing your project's carbon footprint. I will introduce each speaker as they begin, and our first speaker today is Saranya with Slipstream. She will present preliminary findings on her research into secondary glazing retrofits and how existing window systems can be vastly improved with additional glazing, highlighting data, performance benefits, detailed solutions, and the future of this technology and its accessibility. Saranya, take it away.
Thank you, Jason. Hello, everyone. My name is Saranya Gunasingh, and I'm a senior engineer with Slipstream. I'm going to share my screen real quick. All right. So please let me know if you are able to see my screen.
I could see it, but not in presentation mode yet. Sonia.
Oh, okay. Not sure what's going on. Perfect. Okay, this should work.
There you go.
Okay. All right. So thanks so much for joining the webinar today. This session is about a research we did for ComEd and Nicor gas from Slipstream to look at the benefits of secondary glazing systems. So Slipstream is a mission-driven nonprofit organization with the mission to accelerate climate solutions for everyone. And I wanted to take a moment to thank ComEd and Nicor for supporting the study. So the goal of this study when we went in was to understand the energy savings potential for secondary glazing systems and to characterize the market. What does the market look like in Illinois specifically, generally in colder climates, the zone that we're in, 5A, and to understand how does the market supply channel work, all the way from the manufacturer to the person who specs it, to the designer, to the end user. Who are all these different people that are involved in this chain, and what's the value, benefit, challenges for each of these key stakeholders involved? And if there was significant energy savings from this technology based on this study, then what are ways that we can intervene in the market to make sure this technology is accessible to more people and more buildings can benefit from this technology? So secondary glazing system in brief is what envelope is a retrofit technology, it's an envelope retrofit technology that is targeted towards improving the thermal performance of a poorly performing existing window. So this is for an old leaky building that has a window that is a single pane glass. It's pretty leaky. The thermal performance hasn't been paid much attention to. And typically the solution that's offered in such a situation is a window retrofit. And as we know, anything to do with the envelope retrofit is very expensive, and windows being the most expensive component of it all. But honestly, the solution that is an alternate, but not very well understood so far, is a secondary glazing retrofit, which provides the same benefit as a window replacement, but for a fraction of a cost, and it's very quick in terms of installing the new window. So a single pane can be converted to a double pane or triple pane or a quad pane in more advanced applications. So we basically go from one panel of glass to 2, 3, 4. 3 and 4 are not very common, but 1 to 2 is what we typically see in the market. And secondarily, a double pane window that's leaky or poorly performing can also be converted to a more efficient 3-pane glass, a third pane added on to it. So we went about this study by looking at the literature first. Several organizations, Lawrence Berkeley Lab, Northwest Energy Efficiency Alliance being the leaders in this space. So we looked at some of the literature that they've already put out to see what's the energy savings potential. So we have two types of data points from literature. One is a simulation study, and the second is a field study. A simulation study is when we're building a predictive model of what this retrofit could look like and what's the associated energy savings potential. It's not as thorough as a field study, or I would say that a field study is a more accurate source of information because that's measured data. So you monitor a building for a period of time pre-retrofit where there's, say, a single pane window. And then after a year of monitoring how this building works, you add on a second pane, complete the retrofit, and then monitor this building again for another year to see what's the variation between this baseline existing single pane glass and this retrofit that you just completed. And the variation between the two would show us what the energy savings are. Unfortunately, field data is pretty limited at this point. We have more simulation data, but that's changing rapidly. There's a lot of pilots happening in the Northwest, so we expect to have a lot more field data come in the next year or two. And then the third column is about the building type. This technology is applicable to both residential and commercial building types. My study focused more on the commercial side of things, but you will see that a lot of residential buildings can benefit from retrofits as well. And then the fourth column, which is what we're more interested in, the energy savings. You'll see that the savings has a wide range of variance. It goes from all the way from 4% to some of the larger buildings show 41%. So that doesn't really tell us much about what's the energy savings I can expect if I were to go retrofit a building that I own, or like I'm working on a retrofit project. So there's two key reasons for this large variation in savings that we're seeing. One is the building geometry and the window to wall ratio itself. A smaller building with the low window to wall ratio is going to show lower end of the spectrum in savings versus a very large building with 60% or more window to wall ratio is going to show much higher savings potential. And then the note you will see in the last column that I made, and this was pretty surprising to me when I did the study because I did not expect this going in, is the infiltration reduction potential. When we think about a window retrofit, we fully expect the thermal performance of this window is going to be much higher than what exists. This additional pane of glass can be spec'd to have a higher U value, solar heat gain coefficient, a low E coating, it can have a tint, the percentage of visible transmittance of light can be impacted. There's so many different specifications we can add in to make sure this is a high performance glass. But what I didn't think about going in, and looks like a lot of literature doesn't address this either, is the infiltration component. There, in the few different case studies that I looked at, there is potential to reduce infiltration by 70 to 90%. Now, in our climate 5A, which is a heating dominated climate, infiltration adds on to the heating loads of a building significantly. So that's where a lot of the savings come from. Unfortunately, the simulation studies have not accounted for the infiltration reduction potential, which means consequently, the payback period is much longer. So the energy savings is underestimated and the payback is based on the energy savings. So the payback potential is likely to be much lower than what we're seeing in the literature so far. And in addition to a lot of this energy savings that we're seeing, there's a whole lot of non-energy benefits. An interesting tidbit that I came across while I was doing the study is that secondary glazing was not developed to be an energy-saving product originally. Its application was in government military-owned facilities for blast protection, and also in healthcare facilities for where there are mental health patients for safety's sake, where you have to protect the building from occupants trying to get out of the building and so on. So it has a huge safety factor to it, or that's how it was originally developed. And keeping up with that, in addition to energy savings, we see that there's a lot of non-energy benefits. One, there's no landfill when compared to a window replacement. A window retrofit does not take away any of the existing building components. So the existing frame, glass, everything stays intact. A new layer of glass is added on as an addition to improve the thermal performance. So there's a waste is reduced by a lot. And in some of the field studies, we also see that some studies did a post-occupancy comfort survey and a pre-retrofit comfort survey. So the occupant comfort surveys show us that there's significant improvement in glare reduction as well as improvement in thermal comfort. So when we eliminate these poorly performing windows, there is a reduction in the hot, cold spots in the building. There's an increase in occupant thermal comfort. There isn't so much drafts. And also in an urban area like we are in downtown Chicago, where most commercial office buildings are located, noise reduction is a huge benefit as well. So I spoke to a lot of manufacturers as part of this research, and I also spoke to a lot of customers, and I wanted to present some of the key takeaways from the manufacturer and customer interviews. So without getting into a lot of the specific details, there's multiple different kinds of product lines available across manufacturers and even within the same manufacturers. The secondary glazing can be an interior retrofit, an exterior retrofit with different thermal properties, some specifically for historic buildings, some specifically for glare control or noise reduction and so on. So it's important to have a conversation with these manufacturers, make sure that we're speccing the right kind of product for the building retrofit that we're looking at. Most commonly, the person who is most aware of this technology and has the ability to make the connection between the manufacturer and the client is a general contractor. There is a huge gap in market knowledge right now. There is less awareness about this retrofit technology being as effective as a window replacement, but at a fraction of a cost. So there's a lot of room for education and training across all professionals, but generally the general contractor is the one who's most informed. Again, keeping up with the energy savings theme, the cost of the product also varies quite significantly. You see anywhere between $8 per square foot to $50 per square foot. That depends on, is this product, is this an installed cost or a delivered cost? Some clients choose to self-install, so the installation cost is not a component in this cost calculations. It can be self-installed, it's actually pretty simple, but in certain conditions, larger retrofits or larger window types, then the manufacturer does the installation, which adds on to the cost. A high-rise versus a smaller squat building also plays into the cost factor. Again, the type of product specified, a more complex geometry with an advanced product spec costs more compared to a simple low-E retrofit. The payback periods depends on the fuel price, also impacts it. In a location with the higher fuel price, the payback period is lower. In a location where fuel costs are lower, then your ROI is longer and so on. Some utilities in the Northeast and in the West Coast have incentivized and provided rebates for this technology, which makes it a lot more cost effective for a client to install this product. We're looking at some of what are the options in the Midwest for incentives and financial rebates as well. So again, quick summary of findings from the market research. The customer typically prefers a low-E retrofit. Again, if you are thinking about speccing this product, make sure you have detailed conversation with the general contractor, talk to the manufacturers about different product lines before making the final decision, and make sure that the ROI cost includes a lot of these different factors that we just discussed. What are the different products? What's the complexity of the product, the price of fuel, the building characteristics, and what kind of unique requirements are applicable to this building. Typically, the government buildings are the super users for this technology because they own the building. So in case there is a longer ROI, they still own the building to see the benefit from this technology. If it's a builder that's, if the building is going to be sold, then there needs to be a detailed analysis of the ROI and who will be the beneficiary of the savings. Lots of non-energy benefits like we just talked about, and any kind of financial incentives are likely to drive higher intake of this technology in the market. The one other significant driver that Michael will also be talking about is the building performance standards. So building performance standards, which I'm sure a lot of you have heard about discussions in Chicago, it will require existing buildings to improve their performance over a period of time. And typically when we talk about building retrofits, it's usually lighting and mechanical system retrofits. A key component that's being ignored so far is the envelope retrofits. So building performance standards will establish a target that will kind of mandate us, we start looking into the building envelope performance as well. Leaky envelopes might not be able to meet the targets. So this is a technology that can come in handy in these situations. I talked to some of the customers, like as also aside from the manufacturer interviews. So one super user in the US is the General Services Administration. They already have about 7% of their portfolio retrofitted when single pane buildings to double pane or triple pane buildings. And they also have a lineup of buildings that are currently single pane that they are thinking about retrofitting really soon. So 2 case studies that I was able to talk to the USGSA about, they do have an office in Utah and one in Denver, Colorado. So these 2 are the closely resemble our climate zone among the portfolio of buildings that they have. And they saw a 15% energy savings in both buildings. So overall, after they did their M&B, so this is not a simulation study, this is a field study, which is kind of the data that we're really looking for right now. So at the end of this M&B, they found that an overall 15% energy savings was realized at both of these facilities. And what's even more interesting was that they actually did an interior temperature monitor. So on a 27-degree day, so on a pretty cold day, without the window retrofit, the interior temperature was like 42 degrees versus with the window retrofit, the interior surface temperature was in the 60s. So that was like a 20-degree difference in interior surface temperature on a really cold day, which shows us that the window retrofit is very capable of preventing heat loss through the windows. And GSS estimate based on their monitoring is that the secondary retrofit saves about 90% of heat loss through the windows when a retrofit is involved. And this is a pretty standard office building, 2 floors, so not a whole lot of complex geometry or anything like that. So the installation time was less than 10 minutes per window. So you can compare that to the alternate option, which would be a window retrofit, like a complete pulling out of the existing window and replacement. This is super time effective in terms of the retrofit time. So as the secondary component, GSA also did a simulation of this facility across multiple climate zones in the US. So they just pretend that this building is in different climate zones and what's the impact that we're going to see. And in that particular simulation of climate zone 5A, which is Chicago's climate zone, we see about a 13.5% reduction in total energy use in the building. So that building in Chicago would save about $25,000 per year in annual energy cost with a 6.6-year payback. So that's a really good short payback for this technology being implemented in Chicago. And this is the most recent data we have. This was actually published end of last year. Unfortunate part is the simulation piece does not include the infiltration component. So hopefully with the infiltration added in, there will be higher energy savings and a shorter payback. And another case study in our climate zone, I talked to a building manager at the Madison Municipal Building. This is a large historic municipal building in downtown Madison, Wisconsin. And it was built in the 1920s. It was retrofitted recently with not just with the window retrofits, but it was a whole building retrofit that earned the building a LEED Platinum at the end of the retrofit. So as part of the retrofit, they saw that their energy savings was they hit LEED Platinum, so they got the highest percentage of energy savings. It was harder to pull out the improvement from the windows alone because this was a whole building model. That said, including the windows, their payback was in the 20 to 25 year range. Also very interesting was they did a blower door test for infiltration reduction, and they noticed that that was about a 75% reduction. So pre-retrofit, the infiltration was 0.6 CFM per square foot, and post-retrofit, it was a 75% reduction at 0.14 CFM per square foot. They did mention that in this particular retrofit, the time for installation was much longer because, as you can see from the pictures, these windows are almost a floor high. These are in the standard 3-4 feet tall windows. These are very tall, heavy historic windows. So the replacement took about a day for some of these larger windows. Also, they did a post-retrofit comfort analysis, and they found that there was significant thermal comfort increase and noise reduction in this building. So some of the key findings from the manufacturer and customer reviews is that there is very little awareness in the market, which is the primary challenge for this technology to be more widely adopted. Anytime there is a poor envelope, the immediate solution is to think about a window replacement, and not many people, both the designers, contractors, or from the customer, are aware of this category of retrofits that's available to us. The really nice thing is that if a building is going through a secondary glazing retrofit alone, it does not need a permit from the local government or the municipality or from the city, because this does not alter the building structure in any way. So unlike a demolition that would require a permit, the secondary glazing retrofit does not impact any of the existing structure, and hence it can be done really quickly once the right product has been chosen. Which also, again, limits the opportunity for AE firms to be involved. If a customer is doing just a window retrofit and they don't need a permit, then again, it's kind of a little bit of a challenge there. But if you are looking at a whole building retrofit, and if you are from an AE firm, certainly think about a secondary glazing retrofit compared to a replacement. Few major misconceptions in the market is that it's often thought of as a historic building retrofit application alone. It does not need to be. Historic buildings, there are certain limitations on what you can and cannot do with the facade. So the retrofit allows people to maintain the historic building status without really taking anything away from the building envelope, altering the aesthetics and so on. But it really doesn't have to be. It's applicable to any commercial or residential building that wants to improve its envelope performance. And the cost, also the other misconception is that the retrofit cost is comparable to a retrofit. It is not actually to a replacement. The retrofit is significantly cheaper. There's a little bit, of course, based on the cost variations, but sometimes it's about half the cost of an actual replacement. Once you identify the right product, there's really no challenge sourcing the product because there's multiple manufacturers with different product lines to suit the individual project's needs. And the huge benefit is that the product does not seem to have a significant rate of failure. So talking to the customers or to the manufacturers, they didn't really see the product breaking or seal failures or anything like that. I think people recollected maybe 2 in the last decade or so. That's a really low rate of failure. So pretty good product to install. And there isn't any specific maintenance requirements either. So once it's installed, the requirements continue to be what a standard window maintenance would be. So with that, thank you so much for your time, and I will pass it back to Jason. Thank you.
Thank you very much, Saranya. Our second speaker, Michael, with Cascadia Windows and Doors, will discuss the impacts high-performance windows and doors have on improving the overall performance, sharing resources and tools for us to utilize, also discussing the impacts of step codes and the latest revisions to the product category rules for windows and doors. Michael, take it away.
Hi, Jason and everybody. Thank you very much. All right, so let's get into presentation mode here. All right, well, it's great to be with this group. I'm a little bit removed from the locale, but I'm coming to you from the western coast of Canada, at least today. And I wanted to sort of pick up where Saranya finished talking about technologies for leaving windows in place and improving them, and the significance of that place for the building enclosure, which is all true. We're a manufacturer of new windows, so I'm going to be presenting some information larger scale to understand building performance standards and the effect windows have on them. But of course, I'll be talking about windows in a retrofit application as well. Quick introduction to our company. We manufacture window and door products for both large scale, commercial, multifamily, even industrial applications, as well as residential projects and at performance levels that are appropriate for passive house projects. We also make a thermal spacer products for exterior walls, which won't have much focus over the next 10 or 20 minutes. We're primarily a West Coast company, but really our technology is applicable to all of North America equally. And our company's purpose is to provide simple and cost-effective solutions to ever more stringent energy code requirements. We'll get to that point in a second. This is my agenda for the next little bit. We're going to back up one step and take a broader view of our industry and our buildings, and we're going to look at why are building energy performance standards being either introduced in a new way or updated and newly introduced. And we're going to then look at how these standards differ from anything that has come before. Then we'll focus on windows as well as the flexibility that comes with the new standards and how that relates to windows. For any of our architects or engineers who are amongst us, this could be useful for your future analysis with other projects. We'll look at high performance window options generally, and then I've got 3 project examples to conclude with, which each they're all renovations or retrofits, and they all have a little bit of a different story related to them. So that is all to come. Okay, so quick acknowledgement of why there's a problem with buildings. Well, from an energy consumption perspective, and as a result of that, a carbon emissions perspective, we in the building industry have the biggest part of the problem that we could aim our best efforts to mitigate and to manage. So unlike, for example, transportation and the improvements in vehicle technology that are reducing carbon emissions, as part of either building owners, building managers, or architects and engineers, any of us on the call can actually improve upon carbon emission reduction by focusing on the biggest share of that problem. And before I get into talking about numbers or technologies, I want to sort of get a poll going here with the crowd. What I want to do, and this is the audience interaction slide I'm going to do, I'm going to give some clues to everybody here for the 3 buildings, one after another. These clues will describe the building's enclosure, and I want everybody to guess what is the overall thermal resistance, the R value of that building enclosure. And Katie's going to put a poll on the screen with multiple choice answers. So clues for the first building. This is a building over 85 years old on the west coast of North America. It has a brick veneer over top of a steel framed wall. In that steel framed wall, there is some insulation in the steel framed cavity. The windows that you see, punched windows, not a huge window to wall area, they are neither brand new nor are they original. They're somewhere in between. And the small roof deck areas you see also have some insulation. So I know those clues are vague, but anyway, collect them together in your head and have a guess at what would be the overall building R value of that building exterior. And Katie, you can put the poll up there. Thank you. So pick one of those R value ranges you think that this building falls into. We're going to leave that up for about 10 seconds. And as a presenter to a webinar, thank you everybody who's going to press a button and submit an answer, because it's great to see a little bit of interaction with the audience. Okay, Katie, you can close this poll and then let's share the results so everyone can sort of see themselves in the data. Brilliant. Okay, we can close this poll and I'll give the clues to the second building. I'll give the answer at the end. The second building is about a 35-year-old small high-rise multifamily residential building. Half of the exterior, about 50% of the exterior, is concrete. So it's a mass concrete structure. Inboard of the wall areas, there is a steel framed wall, and in that steel framed wall cavity, there is R13 fiberglass batt insulation. The other half of the exterior, the other 50%, is windows. These windows are aluminum framed, double glazed, not thermally broken. Okay, let's put up poll number 2. What do you guys think is the R value for this building? All the responses are the same in this poll, the same as the previous one. Let's just leave that up there a few more seconds. All right, Katie, let's see ourselves in this this data. Interesting. So from a optimist versus pessimist standpoint, this newer building is actually not meeting people's expectations for performance. We're trending downward here. Okay, let's close that poll and go on to the last building. Building number 3 is a much more modern building, but it has a lot more glass. It is a high-rise. It has a window wall system covering virtually the entirety of the outside of the building. This window wall system has a thermal break in its aluminum frame, and it has double glazing. It also covers up the concrete slabs with a little bit of insulation. The slabs are exposed at the small stacks of balconies. Okay, that's the clues for building number 3. Let's have the last poll. And just maybe 5 seconds to enter your best guess. All right, let's see the results of that last poll. Interesting. Much bigger spread. Okay, well, we can close that poll, and I'm not sure if I'm going to validate or disappoint some people there. All 3 of those buildings have R values somewhere between R2 to R3.5, which was the second guess in all cases. Another point about that is that the highest performing part of that R value range is the oldest building. Moving from left to right to the newest building is the bottom of that range, which tells us that, well, a couple of things. Number one, our construction industry hasn't really been setting buildings up to be all they can be from an energy performance perspective. But number two, and the reason behind that is that if you don't regulate something, it does not change en masse. We haven't been regulating building energy performance, and we've not been achieving that unless a building is built for an owner who is opting for that better performance. For everybody's sort of picturing what that R value looks like in physical terms, right in the middle of that R value range would be the R value of a decent fur coat. So take that for what it's worth. But my point about regulations is that we are actually now starting to have different locations around North America dictate better performance from buildings. And that's great. And that will bring us the future we want for our built environment. But regulatory changes have to be based in reality. First, you have to have the technology, then you can mandate its use. You can't do it the other way around. It doesn't work. So new technology will enable more regulations to become more stringent over time for the eventual good of us all. And there's examples of this. For anybody who's interested in codes and standards themselves, this is my little visual on how new building energy standards are changing and compared to how they were before. And this is actually the case really all over North America, regardless of the name of the building energy performance standard that is in force in your locale. They all are sort of based in the same physics, and they all work in a similar manner. And this is pretty new. In comparison, what did we have before? Well, we had energy codes all over the place before, and they applied most of the time, but they were prescriptive in their approach. They would have a recipe saying, for example, insulative target for wall assemblies, and a separate insulative target for roof assemblies, and further a separate target for windows. And not really much attention was paid to how those go together, and also not really attention was paid to how the whole building performs. But the new energy performance standards have the entire building with just one energy consumption limit. It's like you get a bucket of energy for your whole year. Use it any way you like, but you can't have more. And so right after that, a designer of a new building thinks, well, if I have as little amount of that energy as possible leaking out of the building exterior, I have the most left over for all the other fun stuff we want to do, the TVs we want to run and the lights we want to keep on. So that is the new approach that building energy performance standards provide for us. And we've seen this work in other standards that have already been in use optionally in the industry. Passive house is an example of that type of code working. And then what happens when we have a stretch code, or in other locales, sometimes referred to as a step code, anyway, a code with levels that become increasingly more stringent over time. It's basically like saying you can get now in the future, you can build the same building, you just get a smaller bucket of energy each time the code is one more level up. Okay, let's look at windows. If we were either retrofitting or building a new building, and we're focusing on the overall R value, the insulation's thermal resistance of the whole building, obviously that's going to be contributed to by the different assemblies. And I want to just put in some numbers here to show the effect of these different assemblies on the whole picture. So if you were to improve only the walls or the windows or the roof of either a new building or an existing building, what effect would that have on the whole building? So I'm going to say that I'm going to take an example in my head of a modern building, large multifamily building, probably a steel frame building in that case. And R15.6, if you look back in the previous energy standards, that was the last prescriptive R value that existed in energy standards. So that's probably about right for a relatively modern building. We're going to say that it has about 60% of the wall area, because the windows, although we all love windows, would, for a modern building that is subject to a new energy code, for example, if you were to build a new building with these ratios, new energy code is going to require you to limit the poorest performing assemblies. I'm just going to put roof in there as 25. And when I say the poorest performing assemblies, I'm going to say a conventional metal framed window, an aluminum framed window, would be about R2 to R2.5. So I'm going to pick a midpoint there. And we can see that if a building had these assemblies at these ratios, we'd have an overall building R value of about 5. That's a heck of a sight better than those 3 buildings where I asked everyone, please guess the R value, but it's not really where you need to be for compliance with a new building and energy code. So if we were to do something like make the walls better, let's say we make the walls R30, like double the R value there. We're increasing the whole building's R value by not even R1. So with this weak link in this picture, it's not really worthwhile making what is already one of the better assemblies better yet. And we could go to the roof and we could add our 25 trillion to the roof, and it won't make any difference at all for the whole building R value. If we were to take this window, and in this example, I've used a metal frame window, and if we were to change that frame for a more thermally performing frame, more thermally resistant frame, like a PVC or fiberglass or a composite window frame, we would have a window that's approaching R4. And we've added less than R2 to the windows here. We've added it to we've improved that assembly that doesn't even represent a third of the building. Yet here for the whole building, we've improved it by R3 by adding less than R2 to the windows. If you take that a step further and you add another piece of glass, if you're putting in a new modern window, you're adding an additional R3 in my example, where I just changed the window performance, and you're adding more than R3 to the whole building as well. So this is the example of how the weakest link will affect the overall building by far the most. After doing this, then it makes all the sense in the world to look at the other assemblies and try to bump them up as well. So for example, if you were to bump that up to 29 or 30, now you're getting some serious improvements, whereas those improvements would have been lost on their effect of a building that had such a weak link in it, like an old window. Okay, so if you were a new developer and you were building a new building, what could you do with a performance like that? Well, you could utilize a better window assembly to preserve window to wall ratio. Newer designs are calling for less and less glazing to meet energy code requirements, but it doesn't actually need to be that way. You don't have to have less, you just have to have better. And for whatever is the form of the building, if it's small building or large building, the same physics applies. I was just seeing in the comments there as well, very, very good. Patrick, one of our attendees, said for many modern buildings, you can flip that 60 to 30 window and wall ratio. That's absolutely correct. In fact, I'm going to go back and talk about that with this slide. You could actually reverse the window and the wall ratio of the building only by using a better window, so that it did not drag down the overall building energy performance as much. You would be unable to do that with a conventional or sort of industry average window. So great point. Thank you for adding that to everybody's chat. Now, when you're looking at the frame types of windows that could deliver these benefits, all frame types are capable of having high performance options. Aluminum windows are less common to have high performance options because from an insulative perspective, aluminum's not a very natural place to start, but some of the more sophisticated technology in aluminum window systems now does make that possible. From a application perspective, residential, use mostly for wood frames, residential and multifamily for PVC. Add to that high-rise and commercial use for fiberglass because it's much stronger than PVC and aluminum. Less single-family residential now, but definitely more of a commercial application. And I see that I'm running a little bit short on time, so I'm going to move to the case studies that I've got towards the end of this presentation, because I think that a lot of value is gained from studying what has been recently done and what were the benefits and what was the decision making of the building owners in these stories. So to wrap up on these three case studies, the first of these is in Ontario, Canada. It is a retrofit of a high-rise building that was owned by the city, is still owned by the city of Hamilton. It's called the Ken Sobel Tower. This was falling into disrepair and was eventually not occupied when the city government said, well, we've got to do something about this. So what we're going to do is we're going to lead with this project example, and these are the existing building photos. They're not the new retrofitted photos. We're going to do a passive house retrofit of this building. So this is quite extensive. This is not a cheap option to improve your own home or something like this, but they actually removed the concrete balconies off of this building as an example of the lengths that they went to improve the energy performance of this building. So here was the building under construction. And interestingly, this building, unlike most retrofits, was unoccupied during the work. So even though the general contractor came to this building and needed to deal with the building they got as opposed to build it and take responsibility for it. They were at least able to treat it like a full-on construction site, which is different than most continuously occupied retrofits. So this is the finished product. This is, I think, North America's largest current passive house certified retrofit. They used triple glazed fiberglass windows in this application. They used Juliet balcony guardrails attached to the window frames in order to avoid having balconies that would otherwise be a thermal bridge to the building envelope as a whole, because of the fact that the balcony would be cantilevered concrete. Second to last case study. So this building was actually the second one in the please guess the R value. And the building itself needed to be rehabilitated primarily because water infiltration was starting to become a problem more than just a here and there issue. It was starting to become a frequent problem. And this is on the west coast of North America. It gets hammered by rain all cold half of the year. The interesting thing about this building is the way that the building engineer who managed the rehabilitation tendered it. So at the request of the owners, they tendered the work as two options. First option, take it all apart, new windows, scaffolding, new cladding on the over top of the concrete walls, put it all back nice and new, and restore the value of the property, because this was in a fairly, or is in a fairly upscale area. The second option was do all that same stuff, but for the technologies that you use, instead of a basic metal framed double glazed window, instead of a basic cladding system on the wall, go back with high performance stuff and figure out what is the cost for that improvement. And then you can study payback. Well, as it turns out, they went for that option. They put triple glazed fiberglass windows on this building. They even over insulated the concrete structure, and they changed the building's energy consumption from $18,000 a year to $2,000 a year for the heating. So that's an impressive reduction. Interestingly, that upgrade to the technology from just industry good practice up to highly energy efficient, premium energy efficiency, was a less than 5-year payback. The difference in the tendered prices from A versus B was less than a 5-year payback, which was excellent. And the last one is a high-rise multifamily building, again, in a coastal environment. And this was rehabilitated with fiberglass windows, including the world's first fiberglass window wall. It was rehabilitated, again, primarily to address leakage issues, but in conjunction with addressing leakage issues, the locale of this building actually requires that large permitted work now conform to the new energy standards in that city. This particular example is in the city of Vancouver. So to take apart the building enclosure and to completely replace it, the replacement must conform to the new energy standards, which is an interesting change in our regulatory environment, but it's logical in the big picture. That's where everything will have to go. The quantity of glass, the percentage of glass, I'm just reversing a couple of slides here, to maintain the energy performance standards without doing a whole bunch of expensive mechanical system upgrades, prevented this building from being rehabilitated with aluminum framed windows. They actually had to use fiberglass frame windows because of their superior thermal performance to avoid a lot of expensive mechanical upgrades that would have otherwise been necessary to conform to the codes. This is an example of a multifamily building that is occupied throughout the renovation that it underwent. In such a case where windows are being fully removed and replaced, that work occurs in the same day. So the buildings get measured, the windows get produced to order, so made to order. And then once the windows are manufactured and delivered, the installer crews remove and replace the windows that they're working on that day by the end of the same day, so that no owner has to go to sleep at night with a big hole in their wall. So I'm going to wrap up with that. A couple of takeaways here. windows have a really big impact. Anything else that you do to the building to improve it will also have a bigger impact once you fix the weakest link, which I've said this a couple of times now, are generally the windows. And I just want to skip to this. When you're thinking about high performance, and especially if you're thinking about how might high performance give me more flexibility in a project where you're subject to energy standards, windows are stopping being a line item. They are more of a piece in a larger energy performance picture, and they are a key piece. So an extra 10% on a window improvement might yield extra 20% savings on something that would have otherwise been larger or more expensive or more difficult to install. You get the picture. So less of a line item, more of a view towards the end goal, just like the new energy codes themselves are written as. So thank you, Jason, handing it back to you. And I see lots of questions in the chat, so we'll all get a chance to address those at the end of our presentations.
Great, thank you very much, Michael. Our third speaker today is Craig with Sustainability Construction and Consulting. We'll present information about the prefabricated envelope retrofit product he patented called Climate Panels, and how that fits into his efforts to create a repeatable plan for sustainably lowering residential energy emissions. Craig, take it away. We can't hear you, Craig.
How about that? Am I there?
There we go. That's it.
You know, unfortunately, I appear to be struck by Murphy. About 30 seconds ago, my headset appeared to stop working, so I apologize. We'll go by room audio here and hope that it works out very well. Let me share my screen and get started. All right. Hello, thank you very much for that that introduction. I very much appreciate it. My name is Craig Schneider with Sustainability Construction, as mentioned. I want to talk a little bit today about what we need to have go on behind decarbonization. This image here is actually, ironically, the backside of Naperville's municipal solar power array. There's a nice array at Naperville's Public Works, 1 megawatt serving the municipality, and it's a great picture and one that I thought would be perfect for this slide. It's a little bit of a big presentation here, so I'm going to try to get everything in. Forgive me if I go quick, but let's see if we can get to anything that we need to in Q&A if I don't get to it here. All right, so first thing first, I truly believe that we need to have a pragmatic approach to how we're going to decarbonize. Current administration's goal has been stated in the past to get the U.S. grid to 80% of its power from emissions-free sources by 2030. I don't think that it's reasonable to expect this to occur without any decarbonization going on from our building stock. And specifically today, we're going to talk a little bit about the residential building supply and how that can be decarbonized. We have 125 million homes or dwelling units in the United States, and half of them were built before 1980. We need to figure out a cost-effective way to reduce that demand. So these are some brief decarbonization stats. Some of the things that I'll get into in just a bit that I think are hugely monumental to remember is that this is not just about the power. This is, you need to think about the power, not just about the project. About 65% of the energy that our projects demand, including electricity generation, is lost due to waste or inefficiency. We need to reduce that demand because that will have the largest impact. And today we're going to use a reference home, a normal, quote, normal older suburban home in the Chicago area that has been modeled to demonstrate 210 million BTU annual consumption. Frankly, we have a massive amount of energy that is being demanded by our residential infrastructure in this nation. And about 1% of our nation's entire energy use is being demanded and consumed not just by homes, but Illinois homes specifically. Homes in Illinois or dwelling units in Illinois demand about 1% of our nation's total energy usage. It's a massive amount of energy, and one of the things that I felt really called by in the last few years is to try to develop strategies to effectively and efficiently decarbonize that 1%. So we talked about the President administration's stated goals of roughly the 80% reduction. Well, how are we going to do that, and why? We really need to systematically develop a deep energy retrofit or a deep retrofit strategy. And the number one way to do that is by reducing our demand. Again, we need to think about the power, not just about the project. Think about it on a larger and a smaller scale, both of them. And decarbonization is truly needed to lessen that overall energy demand and ultimately minimize the industrial energy supply of what we consume regularly. So this is a flow chart that I'm unfortunately not able to devote near enough time to. It is so spectacular. Lawrence Livermore National Lab develops a Sankey flow chart for how all of the energy in the United States, and specifically in what I'm showing in the state of Illinois, is consumed. What the demand is, what the consumption is, and it really has these layers of intrigue that you find yourself getting sucked into. For the sake of our conversation, we're not going to focus on industrial or transportation or commercial consumption. We're going to look at residential. And in Illinois, our residential market annually consumes 641 trillion BTUs of energy. This is everything from electricity generation to natural gas consumption to even some things like petroleum or biomass consumption in our residential sector. One of the key things to focus on, and it's hard to see in the upper left flow chart, but in this blown up version in the center, on the bottom center, is the rejected and the consumed energy factors. What you'll see here is that roughly 33%, about a third of our energy demand for our residences is wasted. It's wasted during electrical generation. It's wasted during transportation to get from the source to where it's consumed. We have this monumental waste of this energy, which ultimately inflates the demand for what we're going to be using at each of our households. So it's something to really think about. We don't just have our, we have a 120,000 BTU furnace that's has an input of 120,000. Well, no, that input at 120 is just at the furnace. We have a massive input as to what is needing to be consumed and ultimately demanded by that furnace that we also need to think about, or anything larger, the furnace, the home, the region, all of that. So it's about a pragmatic approach. Don't just wear those blinders. Look at the entirety of what you're demanding when you use energy. So one thing to remember going here, that normal US house or that normal Illinois house that I mentioned, it has 213 million BTUs of annual energy consumption. That demand, factoring in that loss that I mentioned, is 327 million BTUs. It's just a massive amount of energy that's being demanded for this home, which is consuming a third less than that. So for some understanding, 1 kilowatt hour, that conversion is 3,400 BTU. So that 327 million BTUs equates to roughly 96,000 kilowatt hours annually. And yes, that is a typo, that 27. Okay. So that normal house, this is how that normal house consumes its energy. We're going to look at, again, how this breaks down, what actually is defined by normal. We're looking at about a 1,500 square foot house, modest. 8-foot ceilings, 8-foot basement, 40-year-old vinyl windows, a 9 ACH starting point. And then these graphs are how that home is heated and cooled annually. Well, I guess what the demand is for heating and cooling. So when you're heating a home, the walls are demanding this much. The foundation is demanding this much. The windows are demanding that much. And this is the kilobtu per hour calculation rate that you're going to size your heating and cooling system towards. So we really want to focus on some of these high points. Again, we have a pragmatic approach. So the largest consumers or the largest demands in this home are going to be our above grade walls, foundation walls, windows, and infiltration while heating. And while cooling, we're looking at ceiling and roof loads, or your attic, windows and skylights, and then also infiltration. So a key thing to remember here, some of you might know it by the 80-20 rule, but it's actually Pareto's principle. The majority of progress can come from the minority of work. Again, pragmatism. We don't need to do it all to make a monumental impact. We need to focus on what will do the most good and focus on that. So this normal home's HVAC loads, 61,000 BTUs for heating load, and a little bit less than 2 tons of cooling load, 21.4 thousand. So let's move on. This is how we're going to accomplish it. This is how we can reduce the load to really find out what's going on behind decarbonization when we put together a package to systematically do this. So the first area improved is going to be the attic. We're going to weatherize, air seal, and install blown insulation in that attic, bring it up to an R60 and substantially reduce the air leakage. If you look over on the right-hand side, that photograph with the number 1 on it, that's cellulose insulation, a truly magnificent insulative material, carbon positive. It's made mostly of borate treated or boric acid treated recycled newspapers. The second area improved exterior walls. This is climate panels. This is the product that I've patented for an exterior prefabricated insulation. We're going to take those exterior walls to about R30 and substantially reduce air leakage again. That photo, or what appears to be the photo on the bottom of the screen, is LiDAR output. And then that LiDAR, which is essentially radar using light or lasers to capture what is digitized in the real world. You can take that data and convert it to CAD files or blueprints that you can create something off of and have this ultra high efficient as-built down to about 2 millimeters of accuracy from 50 meters away. Truly a monumental tool and a terrific way to be able to create something like climate panels to insulate the exterior in a prefabricated and highly efficient manner. The third area that we're going to improve will be windows. We're going to look at some of those secondary glazing options that Saranya was mentioning. That top right picture all the way over on the right-hand side represents a residential secondary glazing option, which almost in this case is looking like a second layer of windows on the interior of what was the original window pane or window frame. So this area helps to reduce the U factor, make it substantially more energy efficient. And then in tandem with low E tinting of that glazing, we're going to minimize heat gains as well as improve the U factor and the air leakage. This is a pretty affordable kind of hybrid mentality to improve what Michael was talking about of essentially picking up that low-hanging fruit. We have the largest area for improvement at glazing, and in residential construction, when you're looking at about 15% window-to-wall ratio, improving that can have a great impact on the overall U factor calculation for both the assembly, be it just the wall, or the exterior as a whole. And the fourth item for foundation walls, you'll see that gentleman in the picture carrying a sheet of rock wool comfort board. This is 4x8 sheets of rock wool insulation, the lowest embodied energy rock wool insulation that is on the market today. We're going to install that down 24 inches from top of foundation on the exterior of the foundation wall. 3 inches of that rock wool board, roughly an R13 on the outside of the foundation, just at the top 2 feet, is a 28% load reduction when heating. It's a massive improvement, and since you're not going too terribly deep, you can do this all in one day and oftentimes without completely sacrificing landscaping. You just essentially drive a wedge or like a sod shovel in between the foundation wall and the soil, and you tilt it back. You bring it back a little bit to create a wedge or a slight trench rather than removing the soil completely. And you can get down roughly that foot or so below grade to install this insulation. Shoot it to the foundation wall, and it does this fantastic job of preventing that cold weather or that unconditioned environment from coming in contact with that foundation. So those key materials really is going to be a 1-part foam sealant to do some of the key air sealing. I am not a proponent of high energy or high greenhouse gas emitting materials, but in very specific locations. A 1-part expandable foam sealant does a better job than caulk or does a better job than other sealants, and it's worth that impact to do the job better than some of the alternatives. The secondary glazing, as discussed, rock wool insulation, and then ultimately cellulose in areas where it can handle it appropriately. It can truly handle some of the moisture that it will run into. So next, we're going to take a look back at that normal suburban house, that 213 million BTU per year annual consumption, and we're going to compare this to now the improved envelope. With what was discussed, those areas, we've now reduced that 213 million BTUs down to 130 million BTUs. Over an 80 million BTU per year reduction. And this green line shows where we were before the improvements. And then you can see the drop down on this graph as to where we are after the improvements. There's monumental improvements for things like infiltration. Above grade walls is cut in half. Foundation walls is nearly halved. Ceiling and roofs, the attic insulation takes more than half that load off. When cooling, attic insulation is about 2/3 reduced. And all the other areas here are roughly reduced or cut in half. Massive improvement with these envelope changes. And we've reduced our overall heating and cooling design loads to 37,000 kilobTUs to heat and just under 1 ton of cooling, 11.8. This is strictly an improved envelope has caused these reductions in demand. This is really what's going on behind decarbonization and how we can do it in single family homes. So next, we're going to take a look at what we can do when we're starting to consider mechanical equipment. Remember that original equipment, that 80% efficient furnace and the 10 SEER air conditioner had 130 million BTU year annual consumption after we improved the envelope. If we were to just add high efficiency traditional, a 96% furnace and a 16 or an 18 SEER air conditioner, we'll lower that to 110 million BTU a year. But if we were to install a heat pump, we're going to bring that even further down to 75 million, or a hybrid heat pump while maintaining that existing furnace, we'll lower it even further to 67 million BTUs a year. And this is something that's factoring in not just those envelope improvements, but now that we've improved the envelopes, we can really use that high performance, cutting edge technology to heat and cool our homes more effectively and with such a significant demand reduction on what we're actually calling for. We're roughly at 1/3 of the consumption of what this house is after retrofit compared to the original, quote, normal home. So the photos on the right are some heat pumps that I've helped some homeowners consider here. The photo right in the middle is actually a Mr. Cool mail order heat pump that is a do-it-yourself installation, complete with, you can look over on the far right-hand picture, line sets that are not brazed. You don't need to worry about soldering. You actually have these quick connect line set connections. So even your average homeowner can make this installation a DIY. Really an incredible growth in this market recently with lots of options. So we really want to know what's going on. This is the costs, and these are people who can do it. So we're going to, again, cut that demand by 70% roughly, and it's going to cost you about $2,500 to improve that attic, to air seal and increase that insulation there. It's a contractor in Batavia, Illinois, Intelligent Energy Solutions. This $2,500 contract provides that service. Significantly reduce air leakage as well and can provide ventilation for both the attic and the house in this cost. Exterior walls, climate panels package on the entire home to bring those exterior walls to roughly R30 without anyone ever having to leave while the work is performed. It's about $29,000. Again, this is a product that I've patented, but there are many other options for exterior insulation and even some for prefabricated exterior insulation options. Residentially, that's starting to get a foothold in the market. Windows, this secondary glazing on a home such as this, about $4,500. $4,700 includes both secondary glazing and supplemental low E tinting on southern and eastern walls, or southern and eastern windows, excuse me. So this is two companies, Allied Window out of Cincinnati, which is a company that was featured in some of the data collection for Sarania's work with Slipstream and ComEd earlier. And Sullivan Tinting is a local window tinter. I contacted local tinters to talk about this test project to see if we could get some realistic options for it, and combined those two services, $4,700. Foundation walls, this kind of pseudo excavation in order to slide that new rock wool in, and then to also flash over it to protect that product, $4,400, and that same Intelligent Energy Solutions company will provide that service. Those heat pumps, if you're going to look at hiring a company to do it, Perfect Home Service is a large suburban HVAC company that focuses on energy efficiency and emerging technology and familiarity with those, will provide a dual fuel, kind of a hybrid heat pump and existing furnace installation for $9,200 for a home such as this retrofitted envelope. If you want to do a mail order option, it's $4,900, and you can order yourself a heat pump to do your own dual fuel or hybrid install. Less than $50,000, you can obtain this retrofit on a modest suburban home with these contractors and these bids. So if you want to take out a loan for this, you can get a home loan, 6.5% home loan, a 10-year package, $50,000, $396 a month. It does not cost you less than what your savings are, but this doesn't factor in incentives. This doesn't factor in future energy cost increases or anything of that line. This is a realistic strategy to deep energy retrofit and decarbonize today. If you are someone who's a little adventurous and you want to get yourself a home equity line of credit, prime plus a half a point, $229 a month. And now you're in the market where you're paying for this money, you're paying just the interest on this money. But if you are looking at the cost of energy rising, you're not too far off from the monthly savings being able to pay completely for the cost of that $50,000 line of credit. So just to be completely honest, there are financing options, and you could look at this in a way to try to finance it up front rather than paying for it immediately in one lump sum. Changing the slide, there we go. All right, so backing out a little bit of a macro view as to everything that we've discussed. We want to start in the upper left-hand corner. That starting home, that normal, quote, suburban home had a consumption of 213 million BTUs. We know that source demand was 327 million, back going to electricity generation and natural gas supply. You need 327 million being demanded from the sources for this 213 million BTU consuming home. After we reduced that envelope, we brought it down, the needs or the inefficiency of that envelope, we brought it down to 130 million BTU consumption. And then yet again, when we had our kind of premium mechanical improvement reduction, we look at that now being 67 million BTUs, all the way from 213. This is over a 2/3 reduction of our demand. So that final source demand of 103 million BTU, factoring in all those inefficiencies to supply and fabricate or generate, the electricity and the natural gas going into a normal home, you are now saving. We have reduced the overall source demand by a larger amount than what the main home consumed in the first place. So again, we have reduced that source demand by 224 million BTUs. It is more than what the original home consumed to begin with, less than $50,000. There we go. All right, and then in summary here, just getting back to that goal, that 80% of our power from emissions-free sources by 2030, we really need to do our part to minimizing our demand to make that 80% amount to obtain. Demand reduction is key. We must use less energy regionally. This is pragmatism, people. It's not just net zeroism. We can do more in more homes. We can reduce a larger amount of consumption in more homes if we bring it up to that point of diminishing return and don't go past that. 146 million BTU annually for less than $50,000. So to bring a similar project to net zero would at least double that cost. And that is from a 10-year-old NYSERDA study in Utica, New York, when it was tested to see how much it would really cost to bring normal suburban homes to net zero. So until net zero costs come down, we really need to reduce demand in more projects and not go beyond that diminishing return. So thank you very much. Again, my name is Craig Schneider, Sustainability Construction. A little bit about myself, my company, our products, and then something that is very near and dear to my heart about idealism on the right-hand side. So thank you. And I think we're going to go back to Jason now after I can stop the share.
Thank you very much, Craig. If Michael and Sarani want to join us again, we can have a quick look at some of the questions that have come in during today's presentation. If some of you want to check out the answers in the Q&A section, I know Sarani's been tackling some of the questions that have come in there also already. Sarani, we have a couple more questions for you to kick it off. Quick clarifying question. Did you say whole building infiltration may be reduced by 70 to 90% from secondary glazing?
Yeah, so the one challenge with like putting numbers behind this technology is that unlike new construction where we have a established code baseline, and then we're comparing all of our retrofits, all of our improvements to that code baseline, the existing building conditions can come in like millions of flavors. It can be a really poorly performing building, an average building, and so on. So depending on that, the literature estimates are that it can be, the infiltration impact can be anywhere between like 8 to 90%. The two case studies that we looked at, the two case studies had blower door testing done. The Madison Municipal Building had a 76% infiltration reduction. And then the GSA facility had over, like, I think they had a pretty high, over 70% infiltration reduction as well. So some of the larger, very leaky commercial buildings where there's mass wall and single pane windows, expect the infiltration savings to be as high as, if not more than the thermal performance benefits.
I think you talked about this in one of your case studies, but have there been any estimates on how much of the 50% energy savings comes from infiltration?
Yeah, there's actually one data point. The Center for Energy and Environment in Minnesota tried to quantify that. They ran their energy models first, and then they thought that the SGS retrofit savings was about 10% of the total building energy use. And then they actually did a field retrofit, and they saw that it was 19%. So what they had not modeled, but did on, I mean, didn't model it on site, but what you can capture on site is the effect of infiltration. So look at 10% without infiltration in the model, 19% with infiltration, field measurement. That was like a pretty large study that they did. So, which basically tells us that including the infiltration impact basically doubles the expected savings. Other than that, the field studies haven't really broken out the effect of infiltration. It's like the overall energy impact that you look at in the building. The AERC, Attachment Energy Rating Council, recognizes that this is an issue when we're talking about envelope retrofit. So they're trying to come up with some standardized processes around how do you calculate for infiltration in addition to the thermal performance as well. So if this is something you're interested in, do look up the AERC website. They do have quite a lot of resources listed there. And I think breaking out the mechanical system impact versus infiltration will be a high priority for them near term.
Okay, to maybe expand on that and to reiterate some of the resources you had mentioned, some of our attendees had been during our presentation Googling to try and find some resources for secondary glazing systems. Could you maybe cover some of those manufacturers again and where we can find our attendees can find some more resources?
Absolutely. I just put the link to where this report will be hosted. There's going to be a pretty detailed report on all of the manufacturer interviews and what product lines the manufacturers offer, as well as customer interviews. There's also a link to all of the original resources of literature that I mentioned. It'll all be in the report in that link that I just posted in the chat box right now.
I also, pardon me, if I could jump in here for a quick second, I also have contacted a number of those organizations that were focused in Sarania's report. And I had really interesting feedback from a lot of them about how residential or single family residential is not a market that they've really had a lot of success in the past. And so I think that it would be truly magnificent if this report and subsequent follow-up can start to show organizations that this is a market that they can emerge into. Whereas it's not traditional to single family homes, it still does have a very low cost in comparison and high output benefit. I had very good results from Allied Window out of Cincinnati, not necessarily local to Illinois. And then Alpin Building Products out in Denver, I believe, was another company that had interest residentially, but had just never been welcomed into the market. So it is something that I think could change in the coming years, but it's just not there yet traditionally, I think.
Michael, we have a couple questions for you also. Based on your analysis, is there a sweet spot to target R values for windows?
Yeah, it's a good question. So the R value target sweet spot is going to change depending upon how good the rest of the building is. So if you're dealing with an old building that you're trying to improve, and you're dealing with old walls that may not even have consistent insulation throughout them, then a premium window may actually outperform the building, which really won't do you as much good as a premium window will do in a building where the wall assemblies, the roof assemblies, and everything else are better. A different way to look at that is, how weak is the window as the weak link? If it's very weak compared to other assemblies, then improving it makes the most difference. If it's like a new window is almost as good as the old wall assemblies, then you probably don't have to go that much further. What does that look like in practice? That looks like in practice, if you have an old building and you're not doing anything to the building envelope other than replacement of windows, and it's not a great performing building, double glazing in a new modern window is probably going to get you where you want to go, and triple glazing is an option. Whereas if you have a modern building, or if you're building a new building, triple glazing makes all the sense in the world to bring up the windows as a weak point. Good question.
And Michael, we had one question that asked if you had any cost information to the 3 retrofit case studies that you shared.
Thank you for that question. Unfortunately, I don't have any overall costs on that. They're rather expensive projects. They are being done by either homeowner groups or cities, all of whom are looking at not only the ongoing payback, but also other needs that triggered the work that I presented in the case study. So they were either fixing a building that was leaking, improving a building to restore its capital value for the owners, where an aging building, an out-of-date building may have diminished the property values over some years, and improving it definitely restores that. So that's not just money spent, it's money moved from your bank account or your line of credit into the value of the building that gets improved when you do that type of retrofit. But I don't have exact cost on the projects as a whole.
Great. A couple questions for you. Was geothermal heat pumps ever considered as part of your decarbonization projects?
I think you said my name. Is that right, Jason? Or
Great, yes.
Okay. Yeah, I love geothermal. I have been familiar with it for a number of years, but it is I think a bit too much of an impact to be able to consider for a large scale implementation. So, when you get into suburban projects that don't have a massive yard, being able to get those wells drilled, we still need to decarbonize those. But the impact is just a little bit too large, I think. The cost is there. I assume the cost will continue to come down like so many of these other technologies, but there's just a massive impact on doing this. And one of the key things that I didn't really have the time to cover was that this decarbonization strategy that I'm kind of focusing on here is minimal impact on the occupants. No one needs to leave. You don't need to go live with your mother-in-law for 3 months when you retrofit your house. You're going to do it quickly. You're going to do it really with people only in your home for a day to change around that mechanical system or to measure and install those secondary glazing options. It's not something where there's the huge impact of completely blowing out a backyard. So just something to consider there. I do love the tech. I just don't think that it fits on a massive, large scale adoption strategy.
A couple more questions for you, Craig. Are there any grants, or have you and any of your projects interfaced with grants available to assist in low-income wage earning homeowners?
Yes, there certainly can be. I think that I would be remiss to not mention the IRA, the Inflation Reduction Act, which just passed the Senate this weekend, and I think is going to pass the House this week. There's going to be a lot coming out of that. In Illinois, we have some impacts from CEJA, Clean and Equitable Jobs Act from last September. There is money associated with those projects that I think many of us see coming down the pipeline. With some other people in the chat, I believe, was awarded a Illinois EPA grant that we wrote, last fall and early spring to upgrade the efficiencies of low-income housing in municipals that are not sourced by ComEd, that are municipal electric providers. So there's 31 of them in Illinois that are members of IMEA. And so there is some Illinois direct funding to do that. I believe that was a $2 million grant to improve the energy efficiency for low-income housing in those areas. So there is money available. I don't have the list off the top of my head, but I do certainly think that there will be more coming here in the very near future, I hope.
More questions for you, Craig. How does the $229 a month home equity line of credit loan cost compare to the projected energy savings if you look at the annual energy savings?
Yep, it's a great comment. Right now, it does not. The cost of that money, the cost of financing that money, is not less than the savings we'll see. I think it was somewhere around $165 a month average monthly savings for these improvements. And then that loan is somewhere around $220, $225. So we're in that $55 in the red, but that's without factoring in the likely increased costs of energy moving forward, as well as some of those other incentives that I was just mentioning and that I think are going to continue to pop up here. So there is a single family home tax credit, I believe, which is at $2,000. That is changing. I think the 2,000 may be the changed value within IRA, and then there's other funding available locally. DSIRE.org, DSIREUSA.org has a list of all the active credits and incentives for your area. It's a great website resource.
And where do you think a homeowner should begin if they're ready to start one of these energy assessments and retrofits?
I wholeheartedly support having an energy assessment done by a HERS rater, hopefully, or at least a BPI certified individual, someone who can come in and evaluate your home. My subjective opinion here is that I don't necessarily subscribe to speaking to a contractor or an architect. I generally subscribe to the process of hiring an owner's representative, someone who has no financial benefit by what they're proposing. They can come in and essentially be the educator to the homeowner, someone who's going to walk through a home or just answer a question. A homeowner says, "Boy, I'd really love to lower my energy bills $50 a month," or "I don't know at all what to do in my home. Can you come in and put together a plan?" And an owner's rep, someone who is a HERS rater, a home energy rating, well, we don't need to get into all the different certifications, but someone who's qualified to do that based on a number of different resources can put that plan together and ultimately outline cost, contractors they recommend, a timeline, and a ranked order or benefit that they can see. I would be happy to share with any customers examples of some of these that we need advocates and just trying to make money. We can all make money and get things done appropriately by advocating collectively to get this done properly.
Great. Thank you very much, Craig. I'm going to hand this back to Katie for some closing remarks.
Thanks, everybody. Thanks, Saranya, Michael, Craig, for all of your presentations and answering all of the audience's questions. It's been really active in the chat and in the Q&A, so we'll try and provide a follow-up document with some of those answers as well for folks. But we have 1 minute left, and I wondered if each of you had a closing thought or action item, something for our attendees. If there was one takeaway or thing that you wanted someone to remember from your presentation or your comments, what would that be? And I'm going to start with Craig because he's unmuted.
God darn it. Without a doubt is have a pragmatic approach. You don't need to be an idealist, or there's no benefit to being an idealist unless you can implement it. Don't assume you have to do everything. Understand that one thing you reduce is an improvement, and don't get caught up in thinking you have to do too much. Make a difference, start small, and do another thing and another thing. That's great.
Thanks, Craig. Michael?
Yeah, I'd actually like to supplement that by saying, take a practical approach and have the end goal in mind, so that you don't make decisions by treating things either like mechanical systems, insulation, windows, like line items. Instead of a line item, have the end goal in mind, and then use the technologies that make sense for your situation.
Great. Thank you, Saranya.
Don't ignore the envelope. I think the architects will be really happy to see the activity in the envelope category going on, because it's so ignored compared to like lighting and mechanical systems, and really does not have to be expensive. I think we have a lot more retrofit options that are cost effective and will improve the performance of the building envelope. So look for those options.
Wonderful. Thank you so much. Thank you, Jason, for putting this session together, for Illinois Green and for moderating today. Thank you, Saranya, Michael, and Craig for your wonderful presentations. We'll be following up with a recording of the session, as well as a PDF of some presentations and hopefully their contact information if they're willing to be contacted for the speakers today. Really appreciate everyone's comments in the chat, and hopefully you guys see that you're getting a lot of praise here at the end in the chat. Thank you again. Illinois Green's next event is in person, August 30th, a member breakfast at DIRT. So come and say hi to us in person, and make sure you're on our newsletter to see our next educational programs coming up. Thank you guys, and have a wonderful afternoon.
Thanks, Katie, Jason, everyone.
Thank you.
Bye-bye.
Take care, everybody.
Thanks, Katie.
Thanks, Jason. Bye.
Bye. I'll talk to you soon.
Yep.